Okay, so today we're going to be talking about an important aspect of chemistry, thermodynamics, and specifically we're going to be talking about problem solving with changes in states and changes in temperature. And so for this part of thermodynamics, you only need two equations. And the first of these equations is Q equals mc delta T, where Q is the energy, m is the mass, C is something we call the specific heat capacity, and delta T is just a change in temperature. And so this specific heat capacity, C, is in units of joules per grams times degrees Celsius or Kelvin. It doesn't really matter. What this is saying is this measurement shows how much energy you need to change 1 gram of material's temperature by 1 degree Celsius. So for water, CH2O, that's 4.184 joules per grams degrees Celsius. And so what that's saying is that it takes 4.184 joules to increase 1 gram of water's temperature by 1 degree Celsius. So the second of these equations is Q equals N delta H. Q again is the energy, N is the number of moles, and this delta H is a change in enthalpy. Now what is this term enthalpy? Well, it's quite complicated and we're not going to get into all the gritty nitty details of enthalpy today. So we're just going to focus on the change in enthalpy related to a change in state. So you'll see usually one of these two, you have the delta H of vaporization, which is just the energy you need to change 1 gram of liquid into a gas, or you'll see the delta H of fusion, which is the amount of energy it takes to change 1 gram of solid into a liquid. So let's look at a problem where we actually need to use these two equations. So let's say we had 180 grams of aluminum at, let's say, 600 degrees Celsius. And we drop onto a block of ice. Which is 180 grams at 0 degrees Celsius. Alright, what would be the equilibrium temperature? Well, obviously, this thing is going to melt. And one of the things you need to do in thermodynamics is split a problem like this into multiple mini problems. So the first problem we're going to focus on is how much energy it takes to melt that 180 gram block of ice. So let's do that. When we're talking about changes in states, you'll notice that this block of ice is at 0 degrees Celsius, and we want to convert that 180 grams of ice at 0 degrees Celsius to 180 grams of water at 0 degrees Celsius. So what we're looking for is a change in state. And so we're going to have to use this second equation that we talked about over here, Q equals N delta H. So you'll notice why I used 180 grams, it's somewhat convenient. So 180 grams of H2O, we need to convert that into moles because over here our equation has moles in it. So to do that, just 1 mole, we're going to divide by the molar mass, and so every 1 mole of water has 18 grams. And so, quite convenient, 10 moles of H2O. And now, you'll need to look up this delta H. It's nothing that you can derive or something like that. It's experimentally determined. And so for water, the delta H is 6.0 kilojoules per mole. So let's just look at how much energy that releases. Q is equal to 6.0 kilojoules per mole. Multiply that by the 10 moles of water, and we get the moles cancel out. You have 60 kilojoules, and I want to turn that into joules, so that's 60,000 joules. All right. And so, where did this block of ice get that energy from? Well, it took it from the hot aluminum. The aluminum is at 600 degrees Celsius, and so the ice absorbed some of that energy to turn into water. So the aluminum is now at a lower temperature after this takes place. So what is this lower temperature? Well, since the aluminum is solid to begin with, this is below the aluminum's melting point, and it's solid at the end, we need to use this first equation, Q equals mc delta T, to figure out what the change in temperature of that aluminum will be. Well, we know how much energy the aluminum lost because of conservation of energy. This is a closed system. Whatever energy the block of ice gained, in this case 60,000 joules, is what the block of the piece of aluminum lost. So where Q is in this equation, or up top, I'm going to put it in 60,000. And then we have the mass, which we know is 180 grams. Multiply that by the specific heat capacity of aluminum, again an experimentally determined value. I'm just going to tell you that it's 0.9 joules per gram times degrees Celsius, and the delta T. And so that delta T is 600 minus T. And so I'm going to solve for my delta T. 600 minus T is equal to 60,000 divided by 180, multiply that by 0.9. And that is 370 degrees Celsius. So again, just rewriting what we had before, 600 minus the temperature of aluminum equals 370. So the temperature of the aluminum is just 600 minus 370. It's 230 degrees Celsius. And so what do we have now? Well, what we have is 180 grams of H2O at 0 degrees Celsius with 180 grams of aluminum at 230 degrees Celsius. And now we were asked to find what the equilibrium temperature of this would be. So they're not going to change states anymore, so we're going to have to use that first equation, Q equals mc delta T. Now as they both reach an equilibrium temperature, the aluminum loses energy while the water gains energy. So what we can do is say, look at what happens on the aluminum side. So it has 180 grams, multiply that by 0.9, which is the specific heat capacity, multiply that by 230 minus the temperature final of whatever this system is going to be. That's how much energy the aluminum loses. Well, whatever the aluminum loses, the water gains. So let's look at what the energy of the water will be. Well, the energy that the water gains is 180 grams. Multiply that by 4.184, which is the specific heat capacity of water. Multiply that by just the temperature of the final, because it's TF minus 0, which is just TF. And so I want to get the final temperatures both to one side. So I have 180, multiply that by 0.9, multiply that by 230 minus, equals 180, multiply that by 4.184, multiply that by the final temperature, and I'm distributing this and then pulling it to the other side. So it's a negative here, so it's going to be a positive on the other side, and that's just 180, multiply that by 0.9, multiply that by the final temperature. And so when I factor out the temperature and then divide whatever I have here, I have 180, multiply that by 0.9, multiply that by 230 degrees, divide that by 180, times 4.184 on this side, plus the 180 times 0.9. And so this is the final temperature. And when I solve for that, I get 40.7 degrees Celsius. So the final temperature of that aluminum water mixture will end up being 40.7 degrees Celsius, assuming no energy gets lost to the container or the air or anything like that. So that's how you would use these two equations to solve problems that have changes in states and changes in temperature.